Hey guys, welcome back. We're going to continue on with our CCIE program here. We're going to get more into some Ospf. Last time we did kind of our introduction to Ospf. Now we're going to be taking a look at a lot more detail on the theory. We're going to be taking a look at Ospf single area configuration. We'll be using, it says a 2-hour conversation, but I doubt it's going to take that long. It'll probably take only about an hour. But we're going to be using this topology, which is in your Google Drive share if you want to load it. I also put in the thinQtank software folder the PDF instructions for setting up IOSV on the platform as well. So, and all the IOSV images that you need. So we're actually running IOSV in this case, and we'll see how well it works in this particular case. So I don't have anything configured in this topology yet. We're going to take a look at really just the basic configurations. How do we verify adjacencies? We'll take a look at the database. We're going to take a look at some of the options for configuring our network statements. It's going to be kind of review for what you would have learned in CCNP or CCNA. But we're going to spend quite a bit of time looking at the Ospf graph, which is in fact the Ospf database, and how we can identify routers in that database. We'll talk about type 1 and type 2 LSAs in this case, DR, BDR election, and then also Ospf Priority, and so on. All right? So we don't have any configurations in the platforms as of right now. If I come into R1, for example, and I do a show IP protocols, I can see I'm not running Ospf. Obviously, for the purposes of enabling any routing process or any routing protocol on a router, you want to make sure that you have all of your data link layer connectivity and maybe even verify some of your IP reachability first. So I'm going to do a quick show IP interface brief. And we have our interfaces that are configured. Just to take a look at the topology here, we're going to be running Ospf in this LAN here, 10.10.14, and on this point-to-point link here, 10.10.45, and we'll be running Ospf on these loopback interfaces as well. The loopbacks are going to be there just to simply create some more routes, but we also use loopback addresses for establishing our router ID as well. All right? So let's go ahead and start, first of all, by identifying some of the basic concepts that have to be configured before we can start doing the configuration. We're looking at IPv4 in this case. We're not going to look at IPv6 until a little bit later on with Ospf v3 and address family mode within Ospf. That'll be a different lesson. So let's get started. All right. Now there's two ways that you can actually implement Ospf. And the ways that you choose to implement Ospf will determine essentially how the Ospf process gets advertised. Now obviously things get a lot more complicated when we start talking about multi-area design, because we're going to have different LSA types. We'll have type 4s potentially, or type 5s, maybe even type 7s if we have special area types. We'll have LSA type 3 from our ABRs. Those are our summary LSAs. But for now, because we're only running a single area design, we're only going to see type 1s and type 2s. All right? So I'm going to go ahead and do config T, router Ospf, and I'm going to specify a process ID. Process ID is locally significant, and it simply represents the routing process that's running on the router itself. We could run multiple processes on the router if we choose, if we want to integrate Ospf maybe potentially differently on different interfaces with different routing domains. But in our case, we're going to be simply running a single process. The process is locally significant to the router, so it does not have to match on any of the routers in the topology. We do like to make it match. I mean, it makes sense to kind of make it match, but it doesn't really have to match. Now, if I look under the Ospf process, you can see I have quite a few options for configuring Ospf. I've got prefix suppressions. I've got default information if I want to inject a default route. We'll talk about a lot of these different elements as we move through all of the different lessons. Obviously, we're going to be doing more and more. We're going to have a lesson on summaries, and we're going to have a lesson on how do we modify, say, for example, the numerator in the Ospf metric calculation with the auto cost reference bandwidth command. We'll talk about modifying maybe default metrics. We'll talk about OE1 and OE2 routes and so on. But our goal today is really just to get our basic OSPF configuration, which you can do at the link level or you can do it at the process level. I'm going to show you guys how to implement this at the process level first, and then we will go ahead and start to take a look at what this looks like at the link level. So in order to enable the OSPF process, what I would typically do is do a show IP route connected, so I can see all of my connected interfaces, and I can make a decision on which interfaces that I want to run OSPF on. And if I'm doing this at the process level, I'm going to use network statements to be able to identify what interfaces are going to be running OSPF and what area those interfaces are going to be in. All right? So you can see from the output here, I've got a loopback of 1.1.1.1, and I've got a local LAN interface of 10.10.14.0. I'm going to choose to run OSPF on both of these interfaces, but I'm only going to do it on the first, the LAN interface first. So I'm going to go ahead and put in a network statement of 10.10.14.0, and I'm going to use an inverse mask. It's not really considered a wildcard mask because it does have to be consecutive zeros followed by consecutive ones. But I'm entering my inverse mask of 0.0.0.255. This is very similar to what we saw with EIGRP, where we had the option of entering network statements without a mask, and then we had the option of entering network statements with a mask. And the mask allows me to identify essentially the scope of the network statement itself, okay? Meaning that what interfaces are included in the process, what interfaces are not included in the process. There is a common misbelief that somehow the network statement describes what networks are going to be advertised. That's actually not true. That's only true in BGP, where the network statements in BGP have to match a route within the routing table itself. So our case, we're just simply enabling OSPF on the 10.10.10 interface. So if any interface starts with 10.10.14, it's going to be running OSPF, and then I'm going to go ahead and place that interface into an area. So in essence, I've now enabled OSPF on that particular interface, and if I do a show IP protocols, I can see that the process is running now in OSPF, and it's running in this network here. We don't have any routing information sources yet because we haven't established adjacencies on the other routers just yet to be able to verify that. Now we're going to talk about the adjacency state machine. We did a little bit of that in the last class where we talked about the down state, the init state, the attempt, the two-way, the exstart, the exchange, and the loading and the full. So we're going to take a look at that a little bit in this particular case. But I've enabled OSPF. Now, one of the things that I wanted to mention about this process is that within OSPF, we select something called a router ID. That router ID plays a very significant role in OSPF. EIGRP has a router ID, BGP has a router ID as well, but in OSPF, it's a very, very important concept. Now that router ID is selected in one of three ways. You can manually configure the router ID by using the router ID command, and then I specify the router ID. The router ID is a 32-bit node ID that's going to allow us to identify the OSPF peer in the graph, in the OSPF graph, which is essentially our shortest path tree calculated graph. It can be entered in as a 32-bit number, but it does not have to be an IP address, okay? Now, in the case of MPLS, we were talking about the process ID earlier. In MPLS layer 3 VPNs, the process actually does matter, but for the most part, in the case of regular OSPF, implementing OSPF in our situation, the process is locally significant. However, the router ID is not locally significant. It has to be unique throughout the entire autonomous system. Now, if I do a show run pipe section OSPF, you can see that I didn't actually establish the router ID when I started the OSPF process. Had I started the OSPF process without any active IPv4 interfaces, I would have received an error indicating that the routing process could not start because it could not establish a router ID. So I guess the question then is, how is that router ID established if I don't have it manually configured? And the answer is, it's going to go through a 3-step process. Number one, and I'll just put this in here, it's the manually configured ID. That's the first choice that I'm going to use to be able to establish the router ID. Because I don't have a manually configured ID, then Ospf uses the IP address of the highest active IP address of any loopback interface. All right, that kind of wrapped around there, but you guys get the idea. We're going to use the highest active IP address of any loopback interface. Now, the reason I didn't establish the loopback as running Ospf is because I wanted to go through the process of showing you that the router ID can be selected from an interface that doesn't actually run Ospf. It just has to be in the up state. And if I do a show IP interface brief, I can see that this loopback 0 is in the up state. So that's how it selected the router ID. All right. Now, let's say that I didn't have any loopbacks. Then the third option is to go ahead and use the highest IP on a physical interface. Physical interface. All right. Which in this case would have been 10.10.14.1. Now, generally speaking, in most Ospf implementations, and certainly on the CCIE lab, you're either in the troubleshooting section or the diagnostic section, you may have to troubleshoot an issue with router IDs and conflicting router IDs, or you may have to, in the configuration section, set the router IDs. So we're going to go ahead and set our router ID to 0.0.0.1 for router 1. If I do a show IP protocols, you will notice that the router ID changed in this particular case. This is kind of a unique behavior for this version of code. Normally the router ID is persistent, meaning that it doesn't change until you clear the Ospf process. So if you're changing the router ID and it turns out that the router ID doesn't change in the protocol operation, you can do a clear IP Ospf process. Let's try that again. And that will reset the Ospf process. It'll clear all the adjacencies. And then if you do a show IP protocols, you will see the router ID listed there appropriately. All right. Now I'm going to go ahead and do network 1.1.1.1, 0.0.0.0. I'm going to put this loopback interface into Ospf as well. All right. So I've got Ospf configured on this platform. What I'm going to do now is I am going to configure router 2, router 3, and router 4, but I'm going to do something slightly different in this particular case. I'm going to enable Ospf on these routers using the interface mode rather than the process mode. So I'm going to do it at the link level, not at the process level. The nice thing about doing it at the link level is that it doesn't require you to calculate network statements or even require that the network statements are entered correctly. I do want to talk a little bit more about the network statements from the perspective of, what if I have overlapping network statements? What happens if I have something at the link level? Does that override that conflicts with the process level configuration? So for router 3, router 4, router 2, router 3, and router 4, we'll go ahead and do these routers together. And I'm just going to do a script here. So config T, router Ospf1. And well, we won't be able to set the router IDs in this case. We'll go ahead and let those guys have the router ID of the loopback in this particular case. And I'm going to go into interface loopback 0 and say IP Ospf 1, area 0. So what I'm doing is I'm applying the Ospf process to the actual interface at the link level rather than at the using a network statement and the process level. I'm also going to go into interface gig 00, IP Ospf 1, area 0. All right, so I'll send those commands, and I should see in this case that we got adjacencies. Yep, we got an adjacency on router 4, adjacency on router 3, adjacency on router 2. So let me go to router Ospf 1 and just do a router ID 0.0.0.2. And notice there it says I need to clear the process, so do show IP protocols. It's interesting it says that, and in this particular case, because I had an adjacency in place, it does not reset the router ID, unlike it did on router 1. So I'm going to do a clear IP Ospf process so that that router ID gets set. Show IP protocols, and we can see that we did a soft reset on our neighbor, and our router ID is 0.0.0.2. All right, so let's do the same thing here. Router Ospf 1, router ID 0.0.0.3. Do clear IP Ospf process, and we'll go ahead and reset that process and save the config. I'll do the same thing on router 4, router Ospf 1, router ID 0.0.0.4, do clear IP Ospf process, and yes, and we'll write that config. Now on router 4, I do need to enable Ospf. If I do a show IP protocols, I can see it's running at the interface level on loopback 0 and gig 00, and I can see a list of all the neighbors in that particular topology. So in this case, it looks like everything is copacetic. We're getting a router ID of 2.2.2.2 and 3.3.3.3, but we're waiting for the dead timer to expire for those to be cleared out. Eventually, those will go away, and we'll no longer see those as routing information sources because the information that I've received from them will eventually go away. So now we've got our adjacencies, so eventually we'll see the 3.3.3.3 and the 2.2.2.2 go away. Okay? But I do have, if I do a show IP interface brief, I do have, sorry, show IP interface brief, another interface on my platform, gig 01. So what I'm going to do is I'm going to do a little bit of a, I normally wouldn't do this, but I'm going to do a little bit of a mix and match. All right? Router Ospf 1, and I'm going to make a mistake here and say network 10.10.0.0.0.255.255 area 1. Okay? Now technically that means that I've placed the gig 01 interface into area 1, right? However, if I do a show run interface GI00, that link level command has placed that interface into area 0. Now if I do a show IP Ospf interface GI00, I can see that the interface is actually in area 0, which means that the link level configuration overrides the process level configuration, which is a good thing, right? The link level configuration overrides the process level configuration. Now the other thing that I can do is I can also do maybe a network statement of 10.10.45.0, 0.0.0.255, area 0. Now if I do a show IP, well actually you see the message right here. It says the area changed for that particular interface. It went from area 1 to area 0. So if I do a show run section Ospf, you will notice that I have conflicting network statements in this particular case. The top network statement indicates that the network is in area 0, but the bottom network statement, which is more generic, puts that same interface in area 1. The point that I'm trying to make here, though, is that in this particular case, we are going to use longest match rules, just like we always do with any kind of routing protocol. Interface is going to take precedence, and then longest match rule within the network statements is going to take precedence. Obviously, in this particular case, we probably wouldn't want to go through the process of mixing the configuration or placing, have some configurations where I've got network statements and other configurations where I've got link configurations and so on. Probably want to be consistent with the configuration, and I imagine that that's what they would have you do that's what they would have you do also in the CCIE. Okay. So last thing is router 5 config T. Now I do want to show you another thing here on router 5. Let's say, for example, if I do a show run interface GI01. Okay. Okay, so you can see in this particular case I have a primary address on the interface. Now, oftentimes with any kind of routing protocol or any kind of configuration, you could have secondary IP addresses that are used for the purposes of whatever. I mean, whatever the idea of a secondary address is. The problem is when you're doing a link level configuration, and we enable, let's go ahead and enable the global process first, router Ospf1, router ID 0.0.0.5, and because I don't have it enabled on any interfaces, it accepted that router ID. So if I do a show IP protocols, I can see that the router ID was taken. Had I already had Ospf running, then I would have to reset the process. But I'm going to go into interface gig 01, and I'm going to do an IP address. Let's do a 10.10.45.55, 255.255.255.0 secondary. Okay, so do show run interface GI01. I've got, for some reason, in this particular case, I've decided to put in a primary address and a secondary address. And whatever reason that might be. There's lots of different reasons why you might choose to use secondary addresses. If I do IP Ospf 1 area 0 now on that interface, and I go to router 1, show IP route Ospf, obviously, well maybe not obviously, but in this case, I am going to see that route eventually. I see the 45. Oh, I forgot to enable it on the, yeah, there we go. We got our adjacency. So I should see eventually, I'm missing something here. I'm seeing the 45 subnet, but I'm not seeing the 5.5.5.5. Let me go ahead and add that. Interface loopback 0 IP Ospf 1 area 0. Show IP protocols. What I should be seeing in this case, I've got all my adjacencies, right? There's neighbor 1, neighbor 2, neighbor 3, and neighbor 4. Well, they're not neighbors, they're just routing information sources. Routing information sources are other routers within my area that I'm receiving information from. But I'm curious why I'm not seeing the 55 subnet. Normally, that would be included as part of the Ospf process. Let me do a show IP Ospf database self-originate. So I am originating 3 link counts. Oops. Router. So 5555 is there, 10.10.45 4 is there, well 45.0. Yeah, so it isn't advertising. Maybe it's a change in this particular code, but what I would do is, in the case where that secondary address was being advertised, I would have to come into interface config T interface gig 01, and I would have to say IP Ospf 1 area 0, and then we have an option of secondaries. That's why, because now it's, I was going to say, we can choose to include or not include, and if I choose secondaries, none, it should not be included. So I'm curious why the secondary address was not included. Actually, I know why, because I put it in the same subnet. Yeah. So IP address 10.10. Let's get rid of that address. No IP address. I realized that I put it in the same subnet. All right, and let's just do 46 in this case. IP address 10.10.46.5 or 55 255.255.255.0 secondary. Okay. Now, obviously, in this case, it's not going to be advertised because I put the command show run interface GI01. Show run interface GI01 because I put in the command IP Ospf1 area 0 secondaries none. Now, if I were to take that command out, then that secondary address would show up. So let's go ahead and take that command out, and let's do IP Ospf 1 area 0. All right. So now if I go over to router 1, show IP route, I should see that 46 subnet. Okay. Obviously, you can't have the same subnet because we're already advertising that prefix. We're not going to advertise the same prefix twice just because we have a secondary address that includes that prefix. All right. So far, we've done our basic configuration. Now, what I'd like to do is I'd like to spend some time kind of going into some of the different verification commands that we can use. All right. And this is where we're going to get into maybe a little bit more of the detail, where we're going to talk about what's the process that we go through to verify OSPF operations? How do I interpret the interface or the commands? There's about 5 basic commands that you'll use to verify OSPF. And then we're going to talk about the DR/BDR election. We'll maybe take a look at some Wireshark captures and see what the hello packets look like and so on our multi-access networks and whatnot. So obviously we talked about this in our first lesson of OSPF. There are 3 primary data structures that are tied to OSPF. The first data structure that's tied to OSPF is the adjacency database. And without adjacencies, you're not going to be able to achieve any convergence. It's not going to be possible. You have to have OSPF adjacencies in order to achieve convergence. So that would be naturally the first thing that I'm going to check. Do I have my adjacencies? Show IP Ospf neighbors, and you see we have lots of options. We can do sorted, we can do detailed, summary. We're just going to go with the carriage return in this case. We'll take a look at some of the other options, and then these are all the interfaces that I could potentially have neighbors on. So those are the same types of outputs. But if I look at my neighbor relationships, I can see the first column represents the router ID of the neighbor itself. So in this case, R1 has 3 neighbors, which makes sense. R1 is in this multi-access network. Router 2, router 3, and router 4 are neighbors. Remember, neighbor relationships in our routing processes are within the broadcast domain. Okay? Now, there are a couple of other things that we see in this particular column. The priority column and the state, or this output, the state column. This is the adjacency state machine that OSPF uses. Let's talk about those 2 in a little bit. The dead timer is going to indicate how long I will maintain this relationship with this OSPF peer if I don't receive additional hellos from that neighbor. So within 37 seconds, well, it would change, of course, over time. But within 37 seconds, if I don't receive a hello packet from 0002, I'm going to remove 0002 from my database, and anything that I've learned from that peer is going to get removed as well. The address is the physical IP address on the interface that is establishing the adjacency. So 10.10.10 or 10.10.14.2 is the IP address of the peer, the physical IP address of the peer. Remember, in OSPF, we're using multicast and unicast to exchange and disseminate information. All right? Now, gig 00 is my physical interface that I go out of to establish the adjacency with that neighbor. All right? Now, let me take a snippet of our topology here, because I want to talk to you a little bit about what the other two options represent. Okay? So this is our topology, and you can see in our output here that router 2, we have a full state, and it's listed as a DR other. There are 3 states that a router can be in a multi-access network. It'll either be a DR, it'll be a BDR, or it will be a DR other. Okay? Now in Ospf, they decided to, this is not something that we see in EIGRP, but in Ospf, they decided to create this process on multi-access networks. A multi-access network is where multiple routers share a common broadcast domain. So Ethernet would be an example of a multi-access network. Frame relay, point-to-multipoint would be an example of a multi-access network, and so on. Okay? So rather than having all of the routers form full adjacencies with each other, we elect a chief on that multi-access network called the DR. The DR stands for designated router. Now let's say in this case R1 is the DR. We'll go through the process. It's going to establish a full adjacency with all the other routers within that topology. If something happens on router 4 is going to notify router 1, and then the purpose is, or the responsibility of router 1 is then to notify the remaining routers in that multi-access network. So it's a way for us to reduce the amount of traffic that's being generated in the Ospf multi-access network. This is not done per domain, it's not done per autonomous system or per area, it's done per multi-access network. So in this particular case, we're going to see an election process taking place on this multi-access network and that multi-access network. Now this one I'm going to talk to you about in a little bit. There's no reason to do a DR-BDR election on that multi-access network, even though it is Ethernet. All right? No reason at all. All right? So we will take a look at that process in a little bit. So based on this output, my relationship, router 1, is router 2 is a DR other. Okay? Router 3 is also a DR other. So if I go back to my topology here, router 2 is a DRO, and router 3 is a DRO, and router 4 is a BDR. All right, now that's only for that multi-access network on the left. That means to say that this guy must be the DR, which means that router 1 is the chief. Now the backup designated router is simply the router that's going to take over this process of maintaining the multi-access network in the case that the DR fails. The question is, how did this election take place? How did this election take place? Well, it's based on 2 values. It's based on priority, number 1, and then it's based on router ID, number 2. All right? And if we look at the priority column here, we can identify that the priority is the same for every router within the topology. That happens to be the default priority for Ospf. That number, that priority value, goes from 0 to 255. If the priority is 0, that means you can never be elected as the DR or the BDR. And then beyond that, the higher the number, the more likely it is that you're going to become the designated router. The reason I say likely is because it's not guaranteed. It depends, all right? Now, what if there's a tie? I'll talk about why it depends in a minute. The default is a 1, which all the routers are set to. So what happens if there's a tie in this process? Who becomes the DR? Who becomes the BDR? Router ID is used as a tiebreaker, all right? And again, in Ospf, the highest number wins, lowest number loses. Now, we already identified that we've set the router ID to this guy as 0.0.0.1. This one is 0.0.0.3. This one is 0.0.0.2. and this one is 0.0.0.4. So you're looking at this topology and going, wait a second, how did router 4 then become a BDR and router 1 became the DR? The problem is this process is completely non-preemptive. Non-preemptive meaning that once you've become a DR, you will not lose your status as the DR unless the process goes down, unless the Ospf process stops, or unless the link that you have going to the multi-access network no longer operates. So in this particular case, router 1 became the DR because it happened to be the very first router that I configured in this topology. Router 4 became the BDR because I went through the process of clearing, setting the router IDs and clearing the Ospf process on some of the routers, so that's just how it kind of worked out. The problem with this process is even if I go in and I set the priority, so if let's say I wanted router 4 to become because it has the most connectivity, it's linked to 2 different multi-access networks and so on, I want router 4 to become the DR for that particular topology. I can go into interface gig 00 and I can say IP Ospf priority, and I can set the priority on the interface. So let's say that I've set it to 50, okay? So if I do a show IP protocols, or show IP Ospf interface GI00, I can see that the priority on this interface is in fact 50. In fact, even if I go to router 1 is aware that that priority became 50 because it's advertised in my hello packets. Priority, router ID, area ID, DR, BDR, neighbor list, these are all things that are sent within the Ospf hello packet. But router 4 did not become the DR. Again, because the process is non-preemptive. You can't even make the process preemptive in Ospf. So unfortunately, even though you can kind of control who becomes the DR and BDR by setting priorities and maybe establishing router IDs as tiebreakers, the reality is whichever router boots up first, whichever router starts its process first, that is going to be the DR in the topology, okay? So there's really no guarantee as to which router is going to actually become the DR. The only way that you can ensure that a router does not become the DR is if I come in here to say interface gig 00 and I do an IP Ospf priority of 0. Just because I have a priority of 0 does not mean that I cannot establish adjacencies with other peers. It just means that I'm not allowed to be the DR or the BDR. But again, if I do a show IP Ospf neighbors, we do see in this particular case that router 4 was promoted to the DR. Router 3 was then promoted to the BDR because it was the next in succession based on the router ID. And if I go to router 4 and I do a show IP Ospf neighbors, you can see that router 1 is now advertising itself with a priority of 0. Why would I do this? Well, maybe router 1 is just a crappy router. It's just old, it doesn't have a lot of memory, it doesn't have a lot of CPUs, and so on. All right? Now, one of the things that I wanted to go ahead and show you is some of the other commands that we use to verify the operations of Ospf. Neighbors is one of them, right? So we want to verify our adjacencies, and you can see some other information about neighbors if you do details. You can see, for example, this neighbor here is in area 0. I'm learning about it on this interface. The current state is full. There have been 6 neighbor state changes since this Ospf process has been running. Here is the DR for the network and the BDR for the network. In the hello packet, I'm advertising EBITs and LBITs. In the DBD, the database descriptor, I'm advertising an EBIT, an LBIT, and an OBIT. We will be talking about what those bits mean as we get into more details on the Ospf database in other lessons, okay? LLS options mean, for nonstop forwarding and fast convergence options that we have. The dead timer is due in 32 seconds. The neighbor has been up for 22 minutes and so on. These outputs are relatively simple to read. Some of them are a little bit more robust than others, but generally the outputs are relatively simple to read. If I do a show IP Ospf interface, brief, I can see on this local router which interfaces are running Ospf, okay? And what's the process ID for the interface? What's the area ID? What is the IP address and subnet mask of that physical interface? What's the cost of the interface? We will be talking about metric calculations in one of our next lessons. What is the state of the interface? How many neighbors do I have on that particular interface? F obviously means full. C might indicate that we've gone through a two-way state. There are instances where a router would stay in a two-way state on a multi-access network as opposed to going into the full state. Remember, we talked about that state machine. You go from down to a init, maybe attempt if you're running a NBMA network, to two-way, start, exchange, loading, and full. Let me see if I can demonstrate the concept of a two-way relationship. Show IP Ospf or Ospf neighbor. Yep, we can see it right here. Router 2 and router 1 have formed a two-way adjacency. All right. Now, router 4 and router 3 are the DRs and BDRs respectively. So if I go back to my diagram here, let's clean this up a little bit. So in this particular case, router 4 is the DR, router 3 is the BDR. All right. So router 4 is the DR. And router 3 is the BDR, which means that both of these routers, this is a DR other, and this guy is a DR other as well. All right? Well, we know that we're going to form a full adjacency with the DR and the BDR. The DR is the one that's doing the primary transactions. We're sending data to the DR at 224.0.0.6, and we're receiving information from the DR at 224.0.0.5. But what happens to the relationship between the routers that aren't either a DR or BDR? That's where the two-way state comes in. Now, I don't know if you guys remember from our last discussion when we were talking about the adjacency state machine, the two-way state indicates what? Okay? It indicates that I see myself in your neighbor list, which means that you have sent me a hello packet, I've sent you a hello packet, and we both agree that we can form an adjacency based on the properties that are required for us to form an adjacency, like hello timers and dead timers and area ID, authentication properties, and so on. So because I know that we can become neighbors, then we go ahead and I place you into my neighbor list. Let me see if I can show you that real quick let me do a little capture here on this interface. All right, so as long as I see myself in your neighbor list, then that is going to allow me to identify that in fact you recognize that I could become a full neighbor. We could form a full adjacency. So we're aware of each other, but we just haven't gone into that full state because we're not a DR or a BDR. So if I look at what's coming from router 2, for example, the hello packet from router 2, one of the things that we can see in the hello packet here is the neighbor list. So let me go into the hello packet, and then this is the neighbor list that I'm referring to. So we can see that priority is being advertised. This is the dead timer that I'm advertising. This is the hello interval that I'm advertising. This is the subnet mask. And then these are the list of the neighbors that I represent. This is my LLS block. We'll talk about that a little bit more later on. What are the TLVs? How are the TLVs used for resynchronization and so on? We'll talk about all that when we get into the advanced discussion of LSDB synchronization and so on. All right, so it's okay that those routers are in a two-way state because they're not DRs or BDRs, so we don't have to have a full adjacency between those two platforms. All right, now if router 2, let's say router 3 went down, then router 2 would become the BDR, then we would have a full adjacency with everybody. Okay? So another command that I want to show you guys real quick is the show IP Ospf interface. We just looked at brief. Now let's do a show IP Ospf interface. One of the things that we're going to be talking about, not so much in detail this lesson, but one of the things we'll be talking about in some of the future lessons is OSPF network types. There are technically 6 different OSPF network types in OSPF. You got broadcast, non-broadcast multi-access, point-to-point, point-to-multipoint, point-to-multipoint non-broadcast, and loopback. And in every case, these different network types within OSPF all behave differently. So for example, this particular interface has been recognized as a loopback interface, so it's automatically going to treat it as a stub host. Now we have a /32 address on this interface, but if it wasn't a /32 prefix, it would still be advertised as a /32 prefix because of the network type. And there are lots of cases where we would want to actually change the network types depending on what we're doing within OSPF. And we'll definitely see examples of that in some of the future lessons. There's a bunch of information in this command. We can see the cost of the interface. We'll talk more about the metrics. The cost of this interface is actually technically less than 1, but since there's no floating point math in metric calculations, we have to round it up to 1. We can see for gig 00, for example, the interface is in area 0. It's being recognized as a broadcast interface. And we can see the DR and the BDR in that interface. We can see the hello and the dead timers for that interface at 10 and 40. There are 2 sets of timers by default that OSPF has, and the dead timer is always 4 times whatever the configured hello timer is. You can statically set the dead timer to something differently, but the dead timer is always going to be 4 times whatever the hello timer is. All right. Now the other thing about this is that I like about this output is it tells me who I'm adjacent with, what the role of that particular router is, if I'm doing any hello suppression for a particular neighbor. So that would be, for example, if I'm running passive interface on an interface. How many neighbors do I have on that? What is my adjacency count, and so on. All right. Another helpful command is, oh, and by the way, if we have authentication configured on this interface, right at the bottom of this output, you would see an indication that there's either MD5 or clear text authentication configured on the interface. All right. Let's see, what else? Show IP OSPF. We can look at traffic, of course. That's going to give me all how many hello packets I've sent and how many link state requests I've sent and link state updates. So we can take a look at that a little bit later. We're not going to look at all the show commands right now. As you can see, there are quite a few. Basic one, neighbor. Database is very important. We're going to wrap up our discussion today by talking about database in this particular case. Interface is a very useful one. Timers, also useful. And topology info is going to be useful as well. Now, if I do a show IP OSPF with just the carriage return, this is also a very useful output. These are all commands that you should be extremely familiar with when you're troubleshooting OSPF in the CCIE lab. You're going to have to know these commands. You're going to have to know how to find information about the topology. It's extremely important. Extremely important. All right. This is probably one of the most useful commands as well because it does give you lots of information about the process. You know, are we going to be able to do BFD and fast restart or graceful restart between our peers based on local link signaling? Let me see what else here. Let's see. Exchange to loading. How long did that take? Right. The other thing that's actually useful here is down here. How many times has the shortest path first algorithm been run in this area on this router? Obviously, we don't want to really see that number increment significantly because that means that we have some sort of convergence problem on the routers. All right. We're not by any means done with looking at these different outputs. Okay. There's many different outputs, and of course we've got another 6 or 7 lessons on OSPF where we're going to do a deep dive into a whole bunch of different concepts. But And we'll be revisiting all of these outputs as we go through those lessons. The last thing that I want to talk to you guys about in this particular case is how do I analyze the database itself, okay? What is it about the database? Because we talked about the adjacencies, which is the very first thing that I'm going to take a look at when I'm trying to identify what's happening in the network. So we talk about adjacencies. We verify that with our neighbor table. Okay, what was the second thing? Well, I'm going to learn stuff from the neighbors. In EIGRP, we talked about that being the topology table. And in the topology table, I'm basically looking at everything that I'm learning. And then we have our routing information base for EIGRP, which was the routing table. Now, actually, there is, you can certainly do a show IP route, and you'll see the O routes in this particular case. O routes indicate that these are what we call intra-area Ospf routes, what we also call type 1 routes. And we're going to spend a lot of time talking about LSA types. We'll start today and then we'll continue on as we get into more advanced topologies. But these are the routes that Ospf is using. Now, if I do a show IP Ospf route, which is a little bit different, this is the routing information base for Ospf. And what this is indicating is very much like a BGP, show IP BGP. When you do a show IP BGP, you're looking at the BGP table or the BGP database. It's essentially the routing table. It's very similar to what we see in BGP. An asterisk indicates that it's a valid route. A greater than symbol indicates that it's a route that's actually installed in the routing table. So Ospf knows about 10.10.14. It's in the Ospf routing information base. So this is kind of like a topology table, if you will, but it's not in the routing table. And the reason why it's not in the routing table is because it's a connected route. So I would say before even analyzing the routing table, we'll take a look at the database and we'll take a look at the routing information base for Ospf. Okay? So let's wrap up our discussion now by talking about show IP Ospf database. Now, this output can get very, very complex. All right? But one of the things that I want you to see is if I run this command, in fact, let me go ahead and just do it on all my routers. Let's do it on all the routers that are in, well, they're all in the same area. So I'll just go ahead and do it on all my routers. Show IP Ospf database. All right? Why didn't it run? Let me try that again. Show IP Ospf database. All right. That's weird. It's not running it. I'll just do it manually. All right, so I've got my database here on router 1. I'll just go over to router 3 here. Show IP Ospf database. And what I want to show you here is that the databases in these routers are essentially synchronized. Let me see if I can get it to kind of line up here a little bit. So this is the database. Let's get that up to the top line and get this up to the top line. So as I switch back and forth, that's router 3, that's router 1, that's router 3, that's router 1, you can see that the databases are 100% synchronized. That happens within the area. Every router within the area, within an Ospf area, should agree on what the topology looks like. Outside of the area, it might not be exactly the same because we're taking our type 1s and type 2 LSAs and we're converting them to type 3s, and we also might see some other type 5s and so on. But when it comes to single area Ospf, all of the routers should agree on the overall topology. Remember, Ospf, unlike a distance vector routing protocol, does not route to networks, it routes to nodes. All right, now what we're seeing in this particular database is router link states and netlink states. So this is the first part of our journey in learning about what LSA types are and what they advertise. Router link states are what we call type 1 LSAs. They're represented in the routing table with an O next to them. A type 1 LSA is generated by each node within the tree, within the domain, to represent the links that are attached to that particular node. So if I look at my topology here, router 1 has 2 links attached. And if I go look at my topology, sure enough, router 1 is attached to the 10.10.14, and router 1 is attached to the loopback. If I look at router 4 is within the area. It should be advertising 3 links. And sure enough, router 4 is advertising 3 links. So essentially, a router link LSA is a type 1 LSA that gets sent to all of the routers within the area to represent all the links that are attached to that particular router. Now, if I do a show IP Ospf database and I type in router so that I can see the details, or I could type in 0.0.0.1 router 0.0.0.1, I can see the type 1 LSAs that are being advertised by router 1. Now, the age is going to indicate how old that particular link state advertisement is. These will stay in the database for 60 minutes. Every 30 minutes, we're going to flood out all of our LSAs. That's called the paranoid update. Every router within Ospf floods their database every 30 minutes. But for the most part, we're doing periodic and incremental updates, and we're only advertising to the peers that need to see the information. So the link state ID in this particular case, it will change depending on the type of LSA. But for type 1 LSAs, the link state ID is the router ID of the originating router. The advertising router is also the router ID of the originating router. If I do a show IP Ospf database, you will see that in some cases, the link ID is not the same as the advertising router. And it really depends on what type of link state advertisement it is. All right, this is where it can get really confusing. And I would say for the most part, for the CCIE lab, you're not really going to have to be analyzing the database too much because they're not going to throw in something where they want you to identify something about a link state advertisement within the lab topology. But on the written exam, they may give you information about a database output where you're going to have to identify what's occurring in the topology only solely based on what exists in this database. We'll do more of this as we move forward and we get into other lessons as well. So this is a stub network. Stub network indicates that it's not a transit link. And in this case, the network type is loopback. And so it's advertising itself as a stub network. This is the network or the address on the link, and this is the subnet mask, and then this is the cost. From that router's perspective, this is the cost of that particular link. All right, and then our next lesson, we'll get into that in a lot more detail. Okay? Let's see, what else? The transit network. All right, the DR, the BDR on the transit network. And notice here, let me do a show IP Ospf database router. So let me see if I can see information about that transit network. Right, it's not giving me details about that transit network. It's saying that I'm connected to that transit network, which is a broadcast domain, broadcast network. This is the DR for the transit network, and this is the BDR. So you're looking at this and going, wait a minute, I don't know anything about that network. There's no cost associated to it, unlike the loopback, where I have a cost tied to it. There is no prefix, and I don't see my address in that link, in that network. That's where the type 2 LSAs come in. All right, but before I get to the type 2, let me just summarize. Show IP Ospf database. These are router link states are type 1 LSAs. They are defined as intra-area LSAs. I'll type that on the screen. Intra-area LSAs. All right? Intra-area LSAs means that type 1 LSAs do not leave the area. So intra-area LSAs are the LSAs that get flooded within an area. When they leave the area, they become inter-area LSAs, which are summary LSAs, type 3s, and the ABRs are the ones that generate those LSA types. We'll get into that in a lot more detail a little bit later on when we get into some of the multi-area design concepts. Okay? So these are intra-area LSAs, and they're represented in the routing table with an O next to them. All right? Now you'll notice if I do a show IP route, and well, let's just do a show IP route. If you look at the code index here, you can see there's Ospf routes, there's OIA routes, there's ON1, ON2, OE1, OE2. We're going to learn about all these different types of routes, but OIA routes are type 3 LSAs. ON1 and ON2 are type 7 LSAs. OE1 and OE2 are type 5 LSAs. Type 7 LSAs are LSAs that come from an ASBR that's attached to a not so stubby area or a totally not so stubby area. E1 and E2 are LSAs that are coming from an ASBR that's attached to a normal area. And the difference between E1 and E2, of course, is how the metric is calculated based on the seed metric that's sent in with the Ospf route. All that stuff we get to look forward to as we get into more of the details. So let's wrap up by talking about now the type 2 LSAs, Show IP Ospf Database, which are the Netlink state LSAs. These are my type 2 LSAs. These are also intra-area LSAs. They do not leave the area, and they are generated only by one type of router in my topology. They're generated by DRs, okay? They don't really represent links. As you can see in the link column, there is no reference to a link count because the purpose of a type 2 LSA is to describe the transit network that the DR is responsible for. So if I do a show IP Ospf database, net, I can see this is a Netlink state. It's got an age of 1435 seconds. The link state ID is the address, the IP address of the DR on that transit network. So that's the physical IP address of the DR's interface that's managing that transit network. This is the router ID of the DR. Checksum, of course, verifying the integrity. I can see the prefix for the transit network here. And then I can see all of the routers that are participating in that multi-access network. So router 4, router 1, router 2, and router 3. So the purpose of a type 2 LSA is to simply advertise what the composition of that transit network is and who's a member of that transit network. Now, there really is no need in the case of our topology to do a DR-BDR election on this link here between router 4 and router 5. Router 4 and router 5 are running broadcast. That is an Ethernet network, so Ospf is automatically discovering that network type as broadcast, so there is a DR-BDR election on that link. For a convergence standpoint, from a convergence standpoint, you really want to kind of reduce the overhead on Ospf as much as possible. You could certainly leave it as a broadcast network, but I think my suggestion would be to build efficiency within the Ospf is to go ahead and change the network type of that interface, of those interfaces, so that we're not doing a DR-BDR election on the interface, and we're not wasting resources by sending those type 2 LSAs, and also maybe potentially increasing the convergence time that's required for those interfaces, okay? So let's go ahead and configure router 4 and router 5 to not do a DR-BDR election on that interface. Now, if I just set the priority to 0 on both interfaces, that would break the connectivity because in a broadcast network, Ospf has to elect a DR-BDR. So if there's no way to elect a DR-BDR, then you're SOL because there's nobody there that's going to claim the DR role. So rather than changing the priority of the interfaces, I'm going to change the network type of the interfaces. Okay? So I'm going to go into interface gig 01, and I'm going to say IP Ospf network type, and you'll see that I have options: broadcast, non-broadcast, point-to-multipoint, point-to-point. I can't set the network type of loopback. I can change a loopback from loopback to another network type, but I cannot change an interface to loopback. And in some cases, let me see if this one has it, you can even do a point-to-multipoint non-broadcast. Right, so that would be the 5th network type. So we've got broadcast, non-broadcast, point-to-multipoint, point-to-point, and point-to-multipoint non-broadcast. If you see a network type of non-broadcast, that means that you cannot do automatic neighbor discoveries if you have a network type that includes non-broadcast in any way, okay? If you have point to anything or broadcast, there has to be a DR-BDR election. Excuse me, not a DR-BDR election, but as long as you don't have the word non-broadcast, you can do automatic neighbor discovery. So let's go ahead and just change the network type, Ipospf network point-to-point. All right, now I will lose my adjacency. All right, I'm going to do a show IP Ospf interface GI01, and I will talk to you about why I lost my adjacency. It should come back up, which it did, because our timers match. Certain network types, and we'll see this in some of the future lessons, but certain network types, the timers will change depending on the actual network type. So I've changed this side to point-to-point. Now if I do a show IP Ospf database, you'll notice here I'm still seeing Netlink states coming from router 5. All right? And that's not what I want to see. If I do a show IP Ospf neighbor, I don't know what that is. What's that beeping noise?
He's testing his bus stream.
Oh. Oh, okay. Come on, man. All right. You'll notice here that I've got a priority of 1, and I've still got full DR-BDR, or full BDR process running here because I haven't changed the network type on this side. So this router still thinks that gig 01 is a broadcast network. Okay? So let's go into interface gig 01. Interface gig 01, and let's change that network type to also point-to-point. Again, you don't really have to do this, but the point, no pun intended, the point here is to kind of reduce the workload that Ospf has as much as possible. All right? And as long as I'm not connecting any other interfaces to this multi-access network, we can run it as a point-to-point link. Now if I do a show IP Ospf database, you will see that I've reduced the number of Netlink states that are being advertised, or type 2 LSAs that are being advertised, by simply changing that network type to point-to-point. All right? All right. Any questions, guys? I know we went 9 minutes past, but that's okay. Do you guys have any questions? Not yet. Sorry? When's the next lesson? Tuesday. All right. Yeah, day after tomorrow. And the next lesson, we're going to go over, we might do 2 lessons. I don't know yet. I'm going to try and figure it out. But yeah, troubleshooting, well, we kind of covered a lot of that in this case. In this lesson, we're going to get into debugs and whatnot. And this lesson is where we start to get into multi-area design, and we kind of dive into what's a type 3 LSA, what's type 4, what's type 5, and so on. Network types, we kind of alluded to some of that today, but a lot of this stuff that we're talking about is overlapping, but that's good. It's good to see it more than once, right? We want to see it lots and lots of times. So you can see that we've got, gosh, how many more lessons of Ospf? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 15 more lessons of Ospf. Actually, 17 more lessons of Ospf. So we spend a lot of time talking about this. All right? and we're going to get into a lot of detail. So I'll send you guys a Slack message. We'll go ahead and coordinate our next event. I appreciate you guys showing up tonight. That's awesome. And I will definitely coordinate a time with you guys by tomorrow so that you have some time to plan. But let's go ahead and tentatively schedule it for Tuesday. Probably around 7 o'clock, I would say, because I am teaching Tuesday. All right?